divide a given square number into two squares. Well, this is very, the a squared plus b squared equals c squared problem. If you have a square number, any square can be expressed as the sum of two squares. Now, you're probably sitting there, wait a minute. 9. How can you write 9 as the sum of two squares? 4. Well, even though in modern mathematics, the branch of mathematics known as Diophantine analysis involves solutions to polynomial equations in which the solutions are integers, whole numbers. Diophantus himself did not have that requirement. His only requirement was that the solutions be rational numbers. And so the problem we looked at was, let me take 16. Okay. Now, this is obviously using modern notation, although, for the record, Diophantus was the earliest known mathematician to have used letters for unknowns and symbols in general terms. We want to divide 16 into two squares. Well, let the first one be x squared. Then the other will be 16 minus x squared. Okay, there's no problem there. It shall then be required to make 16 minus x squared a square. So, completely arbitrarily, our first glance arbitrarily, says, well, take a square of the form ax minus 4 squared, a being any integer, and 4 being the root of 16. For example, let the side be 2x minus 4. And then the square itself is going to be 4x squared plus 16 minus 16x. And you wind up with, let's see, this is a clearer way of looking at it. X squared plus 2x minus 4 squared equals 16, then x squared plus 4x squared minus 16x plus 16 is equal to 16. Now, notice what happens here. At first glance, what kind of an equation is this? Quadratic. But notice, when you cancel the 16, you wind up with x squared plus 4x squared equals 16x. And since we all know that 0 is not really a number anyway, you can factor out the x is equal to 5x squared equals 16x, or 5x equals 16. So x is equal to 16 over 5. And then 2x minus 4 is what, 32 fifths minus 20 fifths, which is whatever you get, 12 fifths. And these give you rational solutions. So this little trick of essentially setting y equal to 2x minus 4 allows you to convert a quadratic equation into a linear equation, and therefore gives you a rational solution rather than some kind of an irrational solution. Question?
Where did the 2 come from?
Ah!
And as
Yeah.
before, why pick 2?
Why pick 2? As a matter of fact, if you use anything so you then have 1 plus m squared x squared equals 8mx. So x would be 8m over 1 plus m squared. And m could be any number except 1. Maybe you-
Any integer?
Any integer, right, excuse me. So now I get confused. The only numbers I really recognize are integers. Positive integers. But the you can express this geometrically by looking at the circle x squared plus y squared equals 16, and by setting y equal to 2x minus 4, you get a line that passes through the point 0, negative 4, and 2 could be replaced with any number greater than 1 up to infinity. You're going to get an intersection point that will have rational coordinates. But that's an excellent question. Why 2, 3, 4, 5, anything would work. And this in fact, if you do the same thing, if you consider Pythagorean triple trinity, a squared plus b squared equals c squared, setting x equal to a over c, y equal to b over c, and do this technique, you wind up with x equal, where you let r be any rational number. It doesn't even have to be an integer. You'll wind up with solutions for x and y, which when you break it on down will give you a equal to 2m times n, b equal n squared minus n squared. I'm not going to go insult your intelligence by going through the solving of the equation. But this at least justifies the, I've already done that. And so there's the theorem that I cited. Now, we go from Diophantus in the 3rd century AD to Pierre de Fermat in the 17th century.